Dear ladies and gentlemen, I'm very glad to welcome you to our webinar, Leverage Reinforced Plastics Durability Prediction from Calibration to Post-Processing. So this webinar's audio will be recorded. You can listen through your computer, and also you can join via calling. This webinar is going to be recorded. The recording will be available upon your request. So about our today's presenters, I'm happy to introduce you to Lucien Duven, who holds a PhD degree in mechanical engineering from Eindhoven University of Technology. He continued his career at Philips Research, investigating topics like biomechanics of the skin and process optimization for stamped glass products. In 2006, he joined DSM, where he focuses on the development of advanced CAE methods for engineering plastics. And I'm also happy to present Pierre Savoyard. He is product manager of Digimat for e-Xstream engineering. So Pierre has material engineering background, and he's strongly oriented towards composite materials and their manufacturing processes. He spent 3 years in the aeronautic industry. He joined e-Xstream engineering in 2015, starting from engineering services team and widening composite challenges portfolio in terms of grade and performances. Currently, he handles a lot of different challenges, SFRP, woven, and NCF, and many, many others. So thank you. Hello guys, can you hear me?
Thank you very much, Anna, for this introduction. Thank you as well, Lucien, to be present today. Okay,
perfect. So I will just show you the next slide to show you how to ask questions in the Q&A session. So as far as you can see, you can click on the question mark, that will open the Q&A window, type your question in the box, and after the webinar is over, I will read aloud the questions we will have time to answer live. But don't worry, all the questions will be recorded, and also if you have any questions, you can drop an email to me or to Pierre or to Lucien. So feel free to do so. Okay, so if everything is fine, I will pass the control to Pierre so that we can start the presentation.
Thank you very much, Anna. So indeed, I should be able to share the presentation for today's webinar. And the real question is, do you see my screen? And do you see only the presenter screen?
We see your screen. Yeah, I do see your screen. Can you do the full screen, please?
So it's supposed to be full screen, so that's why. So what I will do is I'll share only this screen. Is that okay this way?
Yes, perfect. Looking good, Pierre.
Thank you.
I think you're good to go.
Thank you very much, Anna.
Thank you.
So I'm really pleased to be present today to talk about short fiber reinforced plastics and about the effort we've been performing with DSM over the past year. I'm pleased to be here presenting with Lucien Duven from DSM because they played a big role in this work. We are today presenting because we are reaching very close to our 2019.1 release, which is envisioned to be second half of October. So this means that there will be new features present, but there will be new features related to short fiber reinforced plastics, and we want to make sure that all our customers and prospects knows about those features and how to use them. The message in background is for you to witness that integrative approach can work at structural level to predict part lifetime. Similarly to what we are used to do for mechanical performance and failure, the idea is to rely on microstructural description of the composite material in order to predict this lifetime. We envision this because testing of fatigue is something which is challenging, as well as calibration, and as a result, predictions that we are used to make with respect to fatigue model are way too much conservative. So the idea is here to try to bridge the gap and predict a more accurate solution to engineers. So in this mindset, we come with a solution in terms of post-processing and calibration of material card and post-processing environment in order to predict accurate lifetime at part level. The key message for you is, why don't you use Digimat to predict part lifetime at part level for short fiber reinforced plastics? And I would say this presentation would be articulated around three main aspects. The first one being the collaboration that we used, that we had with DSM, and here it will be presented by Lucien. After he will present the work and results he reached and the outcome of this work. I will show you how you can use Digimat-MX in order to calibrate similar material cards in order to predict short fiber reinforced plastic lifetime. Last, I will show you how you can use our Digimat-RP environment for fatigue post-processing in order to compute part fatigue lifetime at FEA level. So with that in mind, we'll start with Lucien's presentation about his work and about short fiber reinforced plastics. Lucien, do you hear me?
Hello, can you hear me?
Yes, I can. I think I will mute and let you keep going.
Yeah, and then you will operate the slides, Pierre.
Sure.
Okay. Yeah, so thanks, Pierre, for the introduction. At this point, I will kind of show our part of the cooperation. So I work at DSM in the Netherlands. DSM, perhaps for you to know, is a global science-based company active in nutrition and materials. And here in the Netherlands, we have our R&D center for the materials business units. And I mainly am active for DSM Engineering Plastics, which has sites of production and R&D around the world, and is mainly active in automotive and E&E segments. And we market our products, the semi-crystalline resins, ranging from PBT to the specialties like the PA46 and PA4T. So these materials are used a lot in automotive, but to push the boundaries there, it's clear that automotive industry will have requirements that we can predict the performance of applications made of these materials. So predictability is really key at the design stage. And together with our partner e-Xstream, we have come a long way over the last years in predicting the static and crash performance of such materials. And now we are also targeting to predict durability and fatigue, because that is really needed to convince automotive suppliers and the industry that these materials can be used to replace metal in a reliable way. So we did a lot of groundwork in understanding fatigue of these SFRP materials. It's great work of many of our mechanical scientists. And about a year and a half ago, we embarked on this joint project with e-Xstream, where we did implement a couple of our elements of our framework for fatigue in the Digimat tools. And Pierre will go into a lot more detail of the tools, but it's really about enabling more accurate part fatigue lifetime predictions. So we want to make the process of the definition of material cards more efficient. So there is work done in the calibration, and features are implemented in Digimat-MX to enable that. And in the end, we also want to enable DSM customers by providing an efficient workflow for the part fatigue lifetime evaluations, and that can now be done in the fatigue life module in Digimat-RP. So how about the prediction results? So that's what I will concentrate on. So in this slide, you basically see all the elements of the framework, and today I will concentrate on the two blue boxes in the right bottom corner. So I will talk about flow simulation and part prediction, and basically go into our validation case. So all the other elements in the definition of the material card and all the inputs that we require to define that as a function of anisotropy and R value, it's something I will not cover today. However, I would be looking forward to meet some of you in 2 weeks from now at the users meeting, where I will give a more complete overview of the complete framework. But for now, we will concentrate first on the flow simulation of this demo part, and then on the fatigue lifetime predictions. So in the next slide, you see, let's say, the first element of that case, where we look into the flow simulation. Pierre, if you could go to the next slide.
I assume I'm sharing slide number 11, focusing on the load bracket.
Okay, I'm on my screen still at slide 10, but okay, you're at slide 11. So then, yeah, there you basically see the load bracket. You also see that we kind of milled a part out of that load bracket, and that's what we put in the micro CT. To measure locally the fiber orientation distribution. And we compared that with the results from the process simulation. In this case, we used MoldFlow. And with the red arrow, you see the location where we probed through the thickness the main diagonal terms of the orientation tensor. And there you see that, especially at the surface, we get a very good estimate of that actual measured fiber orientation. So the dashed lines are the measurement, the full lines are the MoldFlow prediction. And this red arrow is very close to the actual failure location of this part in a fatigue lifetime. So at least for the fiber orientation, we know that we have a good estimate to go into our fatigue calculation as an input. So that's already good to know and to have no uncertainties about that. So then on the next slide, slide 12, I hope you can see the movie. It's, let's say, a movie of the test setup where we load this part in fatigue. It's also good to see the 3 bolts, which kind of fix the part to this steel base plate. And already with tightening the bolts, we apply some stress into the part as well. And we also take that along in our simulation, so that stresses that are in the part before that we load it in fatigue are also included in the analysis. And then we load this part in our lab with different load ratios. So the load ratio in terms of the force is defined as the minimum divided by the maximum force. And on the picture on the right, you see all the measured instances for these 5 load ratios that we've considered. Then if we go to the next slide, we go a little bit more into detail on what that means. So schematically, we have a negative and a positive force direction. And with this definition of the negative force, we can look at the local stresses. And basically, you see at this area on the top picture, we apply a load of minus 1500 newtons. And we have a minimum principal stress in the area where we have failure of the part of minus 34 MPa. Whereas when we load the part in the opposite direction, we get tensile stresses. And those tensile stresses are higher because of that preload that I mentioned that is caused by the pretension in the bolts. So basically it means that the local load ratio at failure based on these stresses is not -1 as is defined by the global forces, but it's less. It's in the neighborhood when we take these values of the stresses of -0.4. And that's important to consider because our model and our material card does consider the effect of the local load ratio. On the next slide, we will go even a bit further because that local load ratio is then also a function of the applied force. I mentioned in the previous one that we applied a load of 1.5 kilonewton. So for the RS -1 case, which are the black triangles, we basically have indeed, we find this value of -0.4, but we also see that that value is really a function of the load that we apply. So it's not only local, but it's also defined by the actual force level that we apply. So all these effects of the load ratio is what we take into account in our fatigue predictions. So also the model does include a sensitivity to load ratio that is defined in the material card and is based on specimen measurements at all these different load levels. Okay then, so how about the predictions then with our approach? So that we can see on slide number 15. And then we see, now perhaps first of all, we represent the lifetime in this graph in terms of predicted lifetime, so predicted NF versus the measured lifetime. So if our predictions would be perfect, all points would need to lie on this diagonal line, but we see that we underestimate the lifetime. And given the range here, we underestimate with a factor of 5 to 30. We do see, however, that as these trends of these lines are parallel to this diagonal, is that we do catch the trend of the measured lifetime with our model. We have to think of the elements that we considered in our calibration, where we handled anisotropy, where we handled the dependence of the load ratio value, and also did a correction for stress concentrations. And for all these elements, we made graphs as we do here for the application. And then we find that we are able to predict anisotropy or microstructure. For any microstructure, we were able to make predictions with our model within a factor of 3. For the R value over a huge range and different microstructures, we were also able to limit that error to a factor of 3. And for the stress concentration correction, we find a factor of 5. So the stress concentration is calibrated on a lot of measurements on notched specimens. So also there we were able to kind of construct these graphs of predicted NF versus measured NF. So given all these factors for these different phenomena that we include, it means basically that this factor of 5 to 30 is kind of what you would expect from all the parts that we individually investigated, like the anisotropy, R value, and stress concentration. However, this was the status early this year, and which was also made available in the previous, or rather current Digimat version 2019.0. So in the meantime, we have been collaborating with e-Xstream on more advanced methods to drive the accuracy further. And now for the next version, they implemented also a correction that accounts for the high level of stresses that you will get at some locations, especially those highly loaded locations that fail. So this was also presented recently by Pierre at the SPE meeting in a joint DSM and e-Xstream presentation. And just a highlight of that, so in the graph with the FEA results, you see a symmetric portion of a notched specimen, where in red you see the high concentrated stress that you will get if you load this specimen in fatigue. And the blue dots in the graph beside it are then the measured lifetime points at certain loads. So with the correction of the stress concentration factor, which is represented here as KF, you see that for the relatively low forces and longer lifetimes, with the blue and the gray line, you get already a good approximation of the measured lifetime. But now with this plasticity correction, we find the red result, and that is definitely a big improvement over the previous results. So we are very happy with this. And the background is that in this case, the basis to do lifetime estimations is a linear elastic stress calculation. So here, basically, we account for those high stress levels that are not realistic with the elastic model to allow for some correction that accounts for the plasticity. So we validated this on the notched coupons and then moved forward also to prove how this improves the predictions on this demo part. So the open symbols were already the results you saw without the plasticity correction. And then next you will see how those predictions improve with the plasticity correction. So there you see that the results of that are now that the predictions are within 1 decade. So this is a great result. We're very happy with this because at the outset we defined this as kind of a goal that we would be very, very happy if we would be able to predict part lifetime within a decade. And given the complexity, I think this is a great achievement of our collaboration. So I want to cover one more item, which is also an important and rather practical one, and that has to do with the mesh size robustness. So we modeled this part with 3 mesh sizes, and then especially did some fine meshing at those failure locations. And we had a original mesh, which we call here intermediate, with a mesh size of 0.5. We made a coarser one with a mesh size of 0.75 millimeters, and a really, really fine one with a mesh size of 0.1 millimeter. And basically here you see that the sensitivity to that mesh size is quite limited. And in our view, it has to do with the fact that we also include the stress gradient correction, which is also affected by mesh size, but kind of counterbalances the effect that we find. So also this kind of indicates that mesh sensitivity is handled in an attractive way and leads to consistent results. Then to summarize, it's good to mention that we have been working on 2 material cards with this framework. So one is of a PA66 material with 50% of glass fibers, and the other one is a PPA material also with 50% of glass fibers. And in kind of hitting this target and investigating this and implementing the framework, we limited ourselves to these 2 grades and characterized them at room temperature and without any moisture. Now, the next steps would be to extend this to more realistic conditions for the material in terms of temperature and relative humidities that are closer to the real applications. So that's definitely one of the focal points. And the other ones is, of course, to confirm the good results on more applications. So we are running more tests on different applications internally and evaluating them together with e-Xstream. But also, if you have any important cases that you would like to consider at this point, yeah, we're open to discuss those type of collaborations. So having said that and having given the overview of our most recent results on our demo case, I give back to Pierre, who will go into depth of the different elements that were implemented in the MX and RP modules. Thank you.
Thank you very much, Lucien, for all those details. Do you hear me?
Yes.
Perfect. So thank you very much for having shared those results and the workflow you deployed to reach those results, and actually those pretty much impressive results, at least from my perspective. I hope it's motivating some of your customers to challenge those mature cards and to look at applications. So I'll remind everyone your email at the end of this webinar so that they can directly contact you. And I remind everyone that those mature cards are available in the Digimat-MX database, so everyone can request DSM to have access to those mature cards via the Digimat-MX database. I will continue this presentation with some more information for everyone about how we modify Digimat-MX to be capable to calibrate such mature card, so that everyone can replicate similar approach of what you did. So for everyone to understand, Digimat, we indeed replicated what we do already for short fiber reinforced plastics in terms of static application for lifetime prediction. So it means we rely on the same approximation using a pseudo-grain intermediate step in the homogenization numerical process that we rely on, thanks to Digimat mean field solver, where we apply indeed at the pseudo-grain the failure indicator. So it's not applied at the phase level, neither at the composite level, but at the pseudo-grain, where here we know precisely the microstructure, because in this hypothetic pseudo-grain, all fibers are fully aligned. So that's where we applied our failure indicator. This failure indicator is indeed similar to what we use for static failure or crash. It's a Tsai-Hill 3D transversely isotropic failure indicator. Instead, here we use it stress-based. And instead of using constant parameters, we here use varying parameters with respect to lifetime, and especially decreasing parameters, which allow us to capture the fact that the failure envelope will be narrower and narrower with lifetime. So you allow less and less stress amplitude with longer lifetime. That's the way you can find this in Digimat-MF to know more in detail how to use those features. When you load such mature card in Digimat-MX for calibration, in addition of stress lifetime curves, you will find the reverse engineering environment here in the reverse engineering tab. And here is the kind of GUI you will have access to. It provides several sections. The first one being similar to static failure and crash failure identification and calibration, which is the failure trigger definition. So it can cover fail thickness fraction, average over the thickness, first fly failure, etc., exactly like as we are used to for static failure. It provides a lifetime target selection where we can focus on a specific lifetime for the calibration and then propagate, you will see, or have a more overview in terms of optimization of the failure indicator. You have then the parameters of this Tsai-Hill 3D failure indicator, so X, Y, and S in terms of strengths. and you have, similarly to what we do for static failure, the localization factor. So you can account for the fact that locally at the coupon, when the coupon is breaking, it is not the macroscopic stress level that is leading to failure, but indeed the local stress, which is higher due to stress concentration at the hotspot. So we can account for this as well. And it is indeed automatically computed in background in Digimat-MX for you. And one thing additional you can find for this calibration of fatigue is the parameter dependency tab on the right-hand side. So it means you can see the X, Y, and S parameter trends with respect to lifetime once you're done with calibration. And when you save your material card, you will then have the load ratio information, which is held by the SN curve you are calibrating on. So you will have this load ratio which is saved, meaning that those parameters are valid for load ratio for a given load ratio, and then you can I would say upgrade this material card, accounting for mean stress sensitivity. To give you more details about how it works, the calibration, you have a short video that has been set up so that you have an idea of how it works. So you find back Digimat-MX interface. It's less new now because, as Lucia mentioned, it was already available in 2019.0. Here is the way you can go through your data for calibration. You have access to microstructure per SN curve as well. So as mentioned, you can select the failure trigger, which allows you to define what you consider as an assumption, and you can select a different lifetime to calibrate. Starting with the first helps, and now we have an evaluation button which allows you to see with those parameters which fit do I get without looping on optimization. If you go for optimization, then you can calibrate for the selected lifetime the failure indicator, meaning you will optimize X, Y, and S so that you have a good fit for this lifetime. So it's not considering the others, but only this lifetime. So you see that the parameters change for this lifetime. If you then switch to all lifetime and propagate this good fit, so estimate from starting values from this calibrated point, it allows you to rely on this good fit for one given lifetime, and based on Euler curves to extrapolate it all over the lifetime, so that you get a first estimate which is already extremely good just based on the Euler curve slopes. That's what it gives. So as you've seen, we only calibrated once, propagated the trend so that it's already giving you a very good fit all over the domain. So it's pretty straightforward. You calibrate once and propagate. And if you're picky, you can then optimize globally each point in order to have a much better fit for all lifetimes. You can see the parameter trends. And then when you will save this model, as I mentioned, you can see that it presents the load ratio. And I think that's it for the Digimat-MX. So I hope this gives you a good overview of how the calibration workflow works and the way you can proceed. It's really similar to what you're used to with respect to static failure, except it's lifetime dependent in the end. Let's now move to the other part of that we've been working on, which is Digimat-RP. Where the goal here is to provide the right environment to post-process lifetime simulations, to post-process FEA simulations in order to reach the good lifetime prediction. Maybe there's a why question to wonder. Why do we need a fatigue post-processing environment? I mean, we don't need it for static failure, so why do we need it for fatigue? The thing is, we tend to make too much assumption with respect to fatigue lifetime prediction, and here we need to account to balance those assumptions, I would say. First, there's the fact that we have a simplistic description of the reality using like faceted geometry, and this leaves whatever the mesh fineness to non-converging local extrema or hardly converging local extrema. The finer you will get, the higher the stresses over the weak spot. So it means that you don't have a converged value of stress with fineness, which is an issue because to identify a lifetime based on this stress field, it's challenging. So that's something we need to live with, and we have to find a way to overcome this aspect. The other aspect is the fact that we perform elastic simulations, while thermoplastics are far too beyond elastic. So it means that when cycling, we don't account for stress saturation due to plasticity, and we neither account for stress relaxation related to viscous effect. And so those two effects would tend to diminish the maximum stresses at the hotspot, which are leading to a certain lifetime. So we would indeed predict higher lifetime if we would be accounting for those aspects. Today we are using elastic simulations, and so we are not. So we are most likely 100% sure underestimating lifetime given of those simplifications. So that's why we need a specific workflow, a specific environment. In Digimat-RP, we provide several workflows in order to trade between time and accuracy for you to estimate part lifetime. The first workflow is the constant load ratio workflow, which means that the load ratio will be considered equal over all elements. It means that we will select an increment, rely on the stress field which is present at this specific increment as the maximum stress, and use it defining a specific load ratio arbitrary from a user perspective that will be applied over all elements. As Lucien mentioned previously, it's really an approximation here because he illustrated that load ratio indeed is varying over the part and is varying with load amplitude. So considering that you can apply a load ratio of -1, whatever the element you consider and whatever the load amplitude you consider is a big approximation. It can work as a first start, but then you may need to go for something else. So you can still do it in order to be really efficient. What you can come with is as well the second workflow, which is that we call the spatially varying load ratio with result assembly. And here, instead of relying on one increment, you will rely on two increments, defining your minimum and maximum phase in the cycle of fatigue you're looking at. And those two extrema will lead to two stress fields, which will be considered as maximum stress field and minimum stress field per element, leading to a different stress amplitude and load ratio per element. So each element which will have its own stress amplitude and load ratio. And this can be varying with the load amplitude depending on the geometric nonlinearity or the boundary conditions effect, etc. So that's here really reaching good fit to really capture the fact that locally the load ratio will be different per element. And there's a third load ratio, which is pretty much aligned with what we were providing already in terms of fatigue, which is a spatially varying load ratio with full cycle simulation, where here, as its name is stating, we tend to describe the full cycle in terms of load amplitude and defining the beginning of the cycle and end of the cycle. Digimat-RP will take care to identify for all elements what is the maximum stress, the minimum stress, and based on those two extrema per element, define the appropriate stress amplitude and load ratio. So here as well, we can capture the fact that the load ratio and stress amplitude will be different per element, and most likely as well depending on the load amplitude. Those three workflows tends to be, as I mentioned, a trade-off between time and accuracy. So on the left-hand side, we tend to say it is really good to go fast, but most likely we make an assumption on the load ratio, so it's not easy. So it's better, I would say, for early design. And when you go toward the right, you see that it's maybe more for validation because you really have a good description of your load cycle, but then you only look at one cycle over the simulation. While if you go for this intermediate result assembly workflow, you can look at different load cycle, and therefore you can perform a load screening to identify what is the worst scenario for your part depending on many load cases. Those workflows are available today in Digimat, or I would say are available, will be available in 2019.1 for Mark Manta, for Mark Solver, for Abacus, and for ANSYS. As I mentioned, we need to correct the lifetime because the lifetime predicted is not the best one, the stresses and therefore the computed lifetime. So we need to correct the stresses or lifetime prediction we make at FEA level. And so for this, we provide different solutions, different corrections. The first one being no correction. So it's really we read the stress and compute lifetime based on those stresses. The second option is a lifetime averaging. It means that over a certain domain, we will account for the fact that there's an extremum which is not, which is most likely underpredicted, and so we will smoothen accounting for surrounding element lifetime, the lifetime of the hotspot. The third option is to go one step further, is to say maybe the stresses were too high, so indeed I will smoothen the stresses and recompute the lifetime in order to have a better lifetime estimate. And if we go further, we can account for the stress gradient correction, which here at first I will describe the interpolation of the stress gradient. The purpose is to say that at the hotspot you will have a maximum stress amplitude direction, and if you look towards the direction in which like the crack will propagate from the hotspot, you will see that you can interpolate a given stress gradient. And here, so the interpolation will consider that at a given distance, I will account for this stress level because I know that at the hotspot it is too high, the stress is too high to compute lifetime. So you basically point one stress level which is lower a bit further in order to recompute lifetime at the hotspot. Another way to post-process this stress gradient curve is to average it over a certain domain or integrate it over a certain domain in order to reach an average stress level which is more acceptable for the hotspot. And the last, one last way we implemented to post-process the lifetime is to say that indeed it is driven by the tangent. So really locally, depending on the stress gradient I have, I will correct the lifetime. And so here you see the function which is used in order to correct the lifetime based on this stress gradient slope. So I hope this gives you a better overview of what are the options available. I will now show you a quick video so that you can see how to post-process, how to use Digimat-RP as an environment in order to post-process part result lifetime. So in Digimat-RP, you will find the post-processing environment from the menu, from the top-down menu. So there's a specific item. First thing you would choose is the workflow, as I mentioned, constant load ratio or varying load ratios. Then you will load the associated FEA results. So here in this case, that's an Abacus file, but as I mentioned, you can use Mark and ANSYS files. You will select the material card of this simulation with the failure indicator. As you can see, it's pointing towards the orientation tensor file. Depending on the workflow, you define the load cycle. So here it's between two increments. And here you can see that we could have corrected for plasticity as Lucien described. And here for local extrema, so lifetime averaging, stress averaging, or stress gradient correction. If we compute the lifetime here, we get a certain number. So here it's pretty low. But then if we post-process the load ratio, you can see what is the local load ratio. So at the dumbbell, it's not relevant, but still it makes sense to see that you can quickly reach it. So changing the load ratio, you will have a different lifetime, which is expected, I would say. So here it's a higher load ratio, so it's a bit different. And then based on the stress field, you can perform a numerical correction. So here, lifetime averaging. And if you look at the stress the lifetime, it's increased because we are softening the effect of the hotspot. So as you've seen, it's not taking much time to reach lifetime estimates, which are accounting for the fact that the hotspot is indeed a over prediction of the stress, so most likely another prediction of the lifetime. So we can easily compute a more realistic lifetime in this environment. Over this presentation, so Lucien took time to present you a part of the work they did. As he mentioned, it will go more in depth at the Digimat user meeting in a few weeks from now. So this work is really impressive, and so I really encourage you to look at this presentation. And so these collaborations led to a great work, and we are happy and really glad to provide the outcomes to all customers here, and really DSM is of good help here, helping us to design the good calibration environment and post-processing environment, as you've seen and as we described. So it means that you can already benefit from material cards, not only from DSM, but as Lucien mentioned, the DSM cards are present. Indeed, Digimat-MX is pretty much growing, almost doubling in number of grades over the past 3 years. And here in the 2019.1 release, we expect about 27 material cards to be released. So that's a big change here. That's really a performance you can now target to design parts. And most likely, Lucien can as well, I mean, everyone can help you. And so material suppliers can guide you in the usage of those material cards as Lucien can support you here. In terms of next steps, first, if you're interested in to know what's new in Digimat, look at the Digimat 2019.1 release webinar. It will be planned in a few weeks from now. As I mentioned, the release is planned for the second half of October. So you will receive a dedicated email for this. If you're interested to work on fatigue, you can already look at the case study to discuss it internally, and don't hesitate to come to us to learn more about it. You can go for your focal point at MSc or e-Xstream, so that we can guide you to go further here. If you're yet customers, you can already benefit from those capabilities, both in Digimat-MX and Digimat-RP. And you can as well access to Digimat-MX material cards, and as Lucien mentioned, those cards are already available. And if you're looking for guidance in order to replicate similar works, you can benefit from our expertise in testing, calibration, and simulation. And for this, I encourage you to contact Thierry Malo, Services Manager. I was really glad to present this work and the available features we provide in 2019.1 release about short fiber reinforced plastics. I was really glad to have Lucien on board to present the result of this work, and we are now available for you if you have any questions. Thank you again.
Thank you very much, Pierre. Thank you very much, Lucien. Now let's see if we have any questions. Okay, apparently everything that we have in questions and answers was related to the webinar quality picture that was all resolved. So we have a couple of minutes now. You can still write a question in the Q&A section. Now I'm getting the control back.
I'm sorry, there were a kind of lag during the presentation. I understood from Lucien. I hope it wasn't. Okay.
Just a little, I would say it was for 15, 20 seconds, but then it was caught up.
Okay.
Okay, so while we're waiting for some more questions to appear, I would like to take this opportunity to thank you so much for being with us today. The recording of this webinar will be available upon request, so don't hesitate to contact any one of us. You can also drop an email at info@e-Xstream.com. Like this, it will be forwarded to me, and I will be able to iterate your question or your comment to the relevant person within the company. And I'd like also to invite you to our Digimat and Material Center Users Conference. Lucian is going to be there, so if you would, and Pierre, of course, as well. So if you would like to ask your questions in person, you will have this opportunity. So our Users Conference is a place where you will be able to learn about our latest updates. You will be able also to meet material experts from all over the world and the presentations of the best-in-class presenters from the industries and also material suppliers. Here you can see a part of the people and companies who are going to be there. We also have a very nice after working hours program. So if you haven't registered yet, please don't hesitate. It's on our website, e-Xstream.com. Okay, so if there are no questions, I would like to thank the presenters again. Thank you, Lucian. Thank you, Pierre.
Thank you.
Okay, so
Thank you very much.
Email address of our marketing manager, Miratod. You can also contact her. Yeah, for the recording, namely. Now I will stop the recording, and I wish you all a pleasant afternoon.
Bye-bye.
Bye.
Thank you very much. See you at the user meeting. Bye.
Thank you. See you.